uh, JUnit Architecture. Here you can see the detailed picture of the JUnit architecture. JUnit is a unit testing framework for the Java programming language. JUnit has been important in the development of test-driven development and is one of a family of unit testing frameworks which is collectively known as XUnit that originated with SUnit. Here you can see the monolithic architecture of JUnit 4, a single jar file. JUnit 4, released in 2006, has a simple monolithic architecture. All its functionality is concentrated inside the single jar file. If a programmer wants to use JUnit 4 in a project, all they need to do is add that jar file on the class path. Here you can see junit.jar file. Here you can see the modular architecture of JUnit 5. A new modular approach was needed to allow the evolution of JUnit framework. The architecture had to allow JUnit to interact with different programmatic clients that use different tools and IDEs. The logical separation of concerns required an API to write tests dedicated mainly to developers, a mechanism for discovering and running the tests, an API to allow easy interaction with IDEs and tools and to run the test from them. As a consequence, the JUnit 5 architecture contains 3 modules: JUnit Platform, which serves as a foundation for launching testing frameworks on the Java Virtual Machine JVM. It also provides an API to launch tests from the console, IDEs, or build tools. JUnit-Jupiter, the combination of the new programming and extension model for writing tests and extensions in JUnit 5. The name comes from the 5th planet of our solar system, which is also the largest. JUnit-vintage, a test engine for running JUnit 3 and JUnit 4 based tests on the platform, ensuring backward compatibility. Here you can see JUnit Platform, junit-jupiter, and JUnit-vintage. Here you can see the big picture of the JUnit architecture. Here all test is connected to vintage, new test is connected to Jupiter, another test is connected to third party, and third party is connected to platform. In JUnit, here in JUnit 5, vintage, Jupiter, and platform is there. Vintage is connected to platform, Jupiter is connected to platform. IDEs and build tools are connected to platform. Here you can see the JUnit 5 technology application architecture. JUnit 5 is a rewrite of JUnit. The following three key building blocks of JUnit 5, along with support for the custom testing framework, which along with their components are represented in this diagram. JUnit Platform, JUnit Jupiter, and JUnit Vintage. Unlike earlier versions of JUnit, JUnit 5 has been split into following 3 sub-projects in addition to the great flexibility of plugging in one's own custom testing engine framework. JUnit platform. JUnit platform is the foundation building blocks of JUnit 5. The most important feature of JUnit platform, which make stand out, is the ability to allow the custom testing framework engine to be plugged in through the testing API. This very capability, the testing API of the platform, allows support for running JUnit test using JUnit 5 testing engine, Jupyter, or any other custom test engine. The following are some of key platform components: testing API for plugging in the custom developed test engine, console launcher for discovering and executing tests from the console, Gradle and Maven plugin support for discovering and executing tests, runner to allow execution of JUnit test in the JUnit 4 environment, junit-jupiter. This provides a test engine for running unit test written with JUnit 5. The following are some of the key aspects of junit-jupiter: programming and extension model for writing unit test and extensions, support for migrating unit test written with Java 4 to Java 4 to Jupyter, JUnit-Jupiter, new assertion methods which work with Java 8 lambdas, support for annotations such as ampersand display name, which allow custom display names consisting of spaces, emojis, special character, and so on. JUnit Vintage provides a test engine for running unit tests written with earlier JUnit versions such as JUnit 3 and JUnit 4. Here you can see a JUnit test connected to junit-jupiter and JUnit Vintage and JUnit and custom testing framework. In JUnit programming model, extension model, migration support, and new assertions annotation are in JUnit-Jupiter. JUnit 3 support, JUnit 4 support, and JUnit 4 support are in JUnit Vintage. Here, custom testing framework. Testing API, JUnit 4 runner, platform launcher, Maven, Gradle-plugin supports are in JUnit platform. Eclipse IDE, Jenkins, Maven, Gradle, and IntelliJ are connected to JUnit platform here. Now we are focusing on all test JUnit. As an example, we can consider this code segment. Here the annotation type ignore. Sometimes you want to temporarily disable a test or a group of tests. Methods annotated with tests that are also annotated with ignore at ignore will not be executed as tests. Also, you can annotate class containing test methods with at ampersand ignore, and none of the containing test will be executed. Native JUnit 4 test runners should report the number of ignored tests along with the number of tests that ran and the number of tests that failed. This annotation is available since version 4.0 in JUnit 5. We use annotation disabled and annotation type ignore is in packaged org.junit. Here on the execution of the class file, the test junit underscore junit1 is skipped during the execution. Besides, the method annotation annotated with ignore and all other test methods run as expected. Here you can see a screenshot of the console window proves the same here. Here you can see the resultant run count shows 3 to 3 test cases, and one test case shows skipped. The run count shows 3 to 3 because even the skip test case attempted to execute. Here annotation type test. The test annotation tells JUnit that the public void method to which it is attached can be run as a test case. To run the method, JUnit first constructs a fresh instance of the class, then invokes the annotated method. Any exceptions thrown by the test will be reported by JUnit as a failure. If no exceptions are thrown, the test is assumed to have succeeded. This is in JUnit 4. As an example 2, we can consider this junit-vintage-engine. Running JUnit 4 test on the JUnit platform here. Just make sure that the JUnit vintage engine here artifact is in your test runtime path. In that case, JUnit 3 and JUnit 4 test will automatically be picked up by the JUnit platform launcher. As an example, we can consider as an exception example, we can consider this code segment here. You can see the optional element expected. Optionally specify expected a throwable to cause a test method to succeed if and only if an exception of the specified class is thrown by the method. If a throwable message or one of its properties should be verified, the expected exception rule can be used instead. This is default to org.junit.test.none.class. The parameter expected declares that the test method should throw an exception. If it doesn't throw an exception, or if it throws a different exception than the one declared, the test fails. For example, here the following test succeeds. Using the parameter expected for exception testings comes with some limitations. Only the exceptions type can be checked, and it is not possible to precisely specify the code that throws the exception. Therefore, JUnit 4 has improved its support for exception testing with assert.assertThrows class throwing runnable and expected exception rule. With assert throws, the code that throws the exception can be precisely specified. If the exception's message or one of its properties should be verified, the expected exception rules can be used. As an error example, we can consider this in JUnit 4. 6 tests pass, 2 tests fail, 2 tests cause an error in error and 8.4s com.mystuff.all test failed, unknown passed, etc., and unknown failed, unknown caused an error, etc. Now we are focusing on Vintage. JUnit Vintage provides a test engine for running JUnit 3 and JUnit 4 based tests on the platform. It requires JUnit 4.12 or later to be present on the class path or module path. Here you can see the monolithic architecture of JUnit 4, a single jar file, junit.jar. JUnit 4, released in 2006, has a simple monolithic architecture. All its functionality is concentrated inside a single jar file. A programmer wants to use JUnit 4 in a project. If a programmer wants to use JUnit 4 in a project, all they need to do is add that jar file on the class path. Here you can see junit.jar. Here you can see JUnit 3.8.x patterns summary. The goals of JUnit. What are the goals of JUnit? First, we have to get back to assumptions of development. If a program feature lacks of automated test, we assume it doesn't work. This seems much safer than prevailing assumption that if a developer assures us a program feature works, then it works now and forever. From this perspective, developers aren't done when they write and debug code. They must also write tests that demonstrate that the program works. However, everybody is too busy. They have too much to do. They don't have enough time to screw around with testing. So the number one goal is to write a framework within which we have some glimmer of hope that developers will actually write test. The framework has to use familiar tools, so there is little new to learn. It has to require no more work than absolutely necessary to write a new test. It has to eliminate duplicated effort. If this was all test had to do, you would be done just by writing expressions in a debugger. However, this isn't sufficient for testing. Telling me that your program works now doesn't help me, because it doesn't assume me that your program will work 1 minute from now after I integrate, and it doesn't assure me that your program will still work in 5 years when you are long gone. So the second goal of testing is creating tests that retain their value over time. Someone other than the original author has to be able to execute the test and interpret the result. It should be possible to combine tests from various authors and run them together without fear of interference. Finally, it has to be possible to leverage existing tests to create new ones. Creating a setup or fixture is expensive, and a framework has to enable reusing features to run different tests. The design of JUnit will be presented in a style first used in. The idea to explain the design of a system by starting with nothing and applying patterns one after another until you have the architecture of the system. We will present the architectural problem to be solved, summarize the pattern that solved it, and then show how the patterns was applied to JUnit. Test case. First, we have to make an object to represent our basic concept, the test case. Developers often have test cases in mind, but they realize them in many different ways. Print statements, debugger expressions, test scripts. If we want to make manipulating test easy, we have to make them objects. This takes a test that was only implicit in the developer's mind and make it concrete, supporting our goals of creating tests that retain their value over time. At the same time, the object developers are used to well developing with objects, so the decision to make test into object supports our goal of making test writing more inviting, or at least less imposing. The command pattern fits our needs more nicely. Quoting from the intent, encapsulate a request as an object, thereby letting you queue or log request. Commands tell us to create an object for an operation and give it a method to execute. To illustrate the evolution of JUnit, we use diagrams that show snapshot of the architecture. Because we expect this class to be reused through inheritance, we declare it a public abstract. For now, ignore the fact that it implements the test interface for the purpose of our current design here, you can think of test case as a long class. For every test case is created with a name, so it test fails, you can identify which test fails. The notion we use is simple. It annotates classes with shaded boxes containing the associated pattern. When the role of the class is in the pattern, it is obvious, then only the pattern name is shown. If the role isn't clear, then the shaded boxes are augmented by the name of the particular participant this class responded to. This notation minimizes the clutter in diagram and was first shown in here. This shows this notation applied to here to test case. Blanks to fill in and run. The next problem to solve is giving the developer convenient place to put their fixture code and their test code. The declaration of test case as an abstract says that the developer is expected to reuse the test class by subclassing. However, if all we could do was to provide the superclass with one variable and no behavior, we wouldn't be doing much to satisfy our first goal, making test easier to write. Fortunately, there is a common structure to all tests. They set up a test fixture, run some code against the fixture, check some results, and then clean up the fixture. This means that each test will run with a fresh fixture, and the results of one test can't influence the result of another. This supports the goal of maximizing the value of the tests. Template method addresses our problem quite nicely. Quoting from the intent, define the skeleton of an algorithm in an operation, differing some steps to subclasses. Template method lets subclass redefine certain step to an algorithm without changing the algorithm's structure. This exactly right. We want the developer to be able to separately consider how to write the fixture, set up and tear down code, and how to write the testing code. The execution of this sequence, however, will remain the same for all tests, no matter how the fixture code is written or how the testing code is written. The default implementation of these methods do nothing. Since setup and tear down are intended to be overridden but will be called by the framework, we declare them as protected. The second snapshot, here you can see the template method here. The template, yeah. Reporting test result. If the test case runs in a forecast, does anyone care about the result? Sure, you run the test to make sure they run. After the test has run, you want a record, a summary of what did and what didn't work. If test had equal chances of succeeding or failing, or if we only ever ran the one test, we could just set a flag in the test case object and go look at the flag when the test completed. However, tests are intended to be highly asymmetric. They usually work. Therefore, we only want to record the failures and a highly condensed summary of the success. The Smalltalk best practice patterns has a pattern that is applicable. It is called collecting parameter. It suggests that when you need to collect results over several methods, you should add a parameter to the method and pass an object that will collect the result for you. We create a new object, test result, to collect the result of running test. This simple version of test result only counts the number of tests run. To use it, we have to add a parameter to the test case.run method and notify the test result that the test is running. And the test result has to keep track of the number of tests to run. We declare the test result method start test as synchronized so that the single test run can collect the result safely when the tests are run in a different threads. Finally, we want to retain a simple external interface of test case. So we create a no parameter version of run that create its own test result. If tests always run correctly, then we wouldn't have to write them. Tests are interesting when they fail, especially if we didn't expect them to fail. What's more, tests can fail in ways that we expect. For example, by computing an incorrect result, or they can fail in more spectacular ways. For example, by writing outside of bound of an array. No matter how the test fails, we want to execute the follow test. JUnit distinguishes from failures and errors. Possibility of a failure is anticipated and checked for with assertions. Errors are anticipated problems like an array index out of bound exception. Failures are signals with an assertion failed error to distinguish and yeah. JUnit comes with a different implementation of test result. The default implementation counts the number of failures and errors and collects the results. The text result collects the results and present them in a textual form. Finally, the UI test UI test result is used by the graphical version of JUnit test runner to update the graphical test status. The test results is an extension point of the framework. Client can define their own custom test classes. For example, an HTML test result reports the result as an HTML document. Now to but subclasses test case again. We have applied command to represent a test. Command relies on a single method like execute called run in the test case to invoke it. The simple interface allows us to invoke different implementation of a command through the same interface. We need an interface to generally run our test. However, all test cases are implemented as a different method in the same class. This avoids the unnecessary proliferation of classes. A given test class may implement many different methods, each defining a single test case. Each test case has a descriptive name like test money equals or test money add. The test cases don't conform to a simple command interface. Different instances of the same command class need to be invoked with a different method. Therefore, our next problem is to make all test cases look the same from the point of view of the invoker of the test. Reviewing the problems addressed by the available design patterns, the adapter pattern springs to mind. Adapter has the following intent: convert the interface of the class into another interface clients expect. This sounds like a good match. Adapter tells us different ways to do this. One of them is a class adapter, which uses subclassing to adapt the interface. For example, to add test money equals to run test. We implement the subclass of money test and override the run test to invoke test money equals. To use the subclassing requires us to implement the subclass for each test case. We put an additional burden on the tester. This is against the JUnit goal that the framework should make it as simple as possible to add the test case. In addition, creating a subclass for each testing method results a class bloat. Many classes with only a single method are not worth their cost, and it will be difficult to come up with the meaningful names. Java provides anonymous inner classes, which provide an interesting Java-specific solution to the class naming problem. With anonymous inner classes, we can create an adapter without having to invent a class name. This is much more convenient than full subclassing. It prevents compile time type checking that at the cost of burden on the developer. Smalltalk best practice patterns describe another solution for the problem of different instances having differently under common heading or pluggable behavior. This idea is to use a single class which can be parameterized to perform single different logic without requiring subclassing. The simple form of pluggable behavior is the pluggable selector. Pluggable selector stores a Smalltalk method selector in an instance variable. This idea is to limit is not limited to Smalltalk. This is also applicable to Java. In Java, there is no notion of method selector. However, the Java reflection API allows us to invoke a method from a string representing method name. We can use this feature to implement a pluggable selector in Java. As an aside, we usually don't use reflection in ordinary application code. In our case, we are dealing with an infrastructure framework, and it is therefore okay to wear the reflection hat. JUnit offers the client the choice of using pluggable selector or implementing an anonymous adapter class also. To do so, we provide the pluggable selector as an default implementation of run method, run test method. In this case, the name of the test case has to correspond to the name of the test method. We use reflection to invoke the method, and first we look up the method object. Once we have the method object, we can invoke it and pass it to argument. JDK 1.1 reflection API only allows us to find public method. For this reason, you have to declare test methods as public, otherwise you will get no such method exception. Don't care about one or many test suite. To get confidence in the state of a system, we need to run many tests. Up to this point, JUnit can run a single test case and report the result in a test result. Our next challenge is to extend it so that it can run many different tests. This problem can be solved easily when the invoker of the test doesn't have to care about whether it runs one or many test cases. The popular pattern to pull out in such situation is composite. To quote this intent, composite objects into a tree structure to represent part, whole hierarchies. Composite lets client treat individual objects and compositions of object uniformly. The point about part whole hierarchies is of interest here. We want to support suites of test. Composite introduces the following participant component. Declares the interface we want to use to interact with our tests. Composite implements this interface and maintains the collection of tests. Leaf represent test case in a composition that conforms to the component interface. The pattern tells us to introduce an abstract class which defines the common interface for a single and composite object. The primary purpose of the class is to define an interface. When applying composite in Java, we prefer to define an interface, not an abstract class. Using an interface, avoid committing JUnit to a specific base class for tests. To all that is required is that the test conform to this interface. test case corresponds to a leaf in a composite and implements the interface as we have seen above here. Next, we introduce the composite participant. We name this class test suite. A test suite keeps its child test in a vector. The run method delegates to its children. Finally, the client have to be able to add test to the to a suite. They can do so with the method add test. Notice how all of the these things only depends on the test interface. Since both test case and test suite conforms to the test interface, we can recursively compose suites of test suites. All developers can create their own test suites. We can run them all by creating test suites composed of those suites. This works fine, but requires to add all the tests to a suite manually. Early adapters of JUnit told us this was stupid. However, you can write a new test case. You have to remember to add it to a static suite method. Otherwise, it will not be run. We added a convenient constructor to test suite which make the test case class as an argument. Its purpose is to extract the test methods and create a suite containing them. Test methods must follow the simple conventions. They start with the prefix test and take no arguments. The convenience constructor uses this convention, constructing a test object by using reflection to find the testing method. The original way is still useful when you want to run subset of test cases only. So here we are at the end of this JUnit tour with JUnit 3.8.x. This figure shows the design of JUnit at a glance, explained with patterns here. Notice how test case, the central abstraction of in the framework, is involved in 4 patterns. The pictures of mature object design shows this same pattern density. The star of this design has a rich set of relationships with the supporting players. Here you can see the test interface here. It's a composite component here. Here you can see 2 subclasses. This test case and test suites is inherited from test. Test case has command pattern, template pattern, and composite leaf here, and pluggable selector. And test suite has a composite, and it has run method and add test method. Test suite composite of tests. Test case has run method, run test, setup and tear down, and pluggable selector fname. Test case is connected to test result. Here it has a collecting parameter pattern, and this one is inherited from test case, and it has this class. This follows the adapter pattern. It has run test method. As an example, we can consider org.junit.vintage. It's in Marmon repository. It's the group ID. here, org.junit.vintage. It's in the group JUnit-vintage. The group description is JUnit-vintage. Here you can see JUnit 3 test case. The class test case, a test case defines the fixture to run multiple tests. To define a test case, step 1, implement a subclass of test case. Step 2, define instance variables that store the state of the fixture. Step 3, initialize the fixture state by overriding setup. So it's already set up. Step 4, clean up after a test by overriding tear down method. Overriding tear down. Each test runs in its own fixture, so there can be no side effects among test runs. For each test, implement a method which interacts with the fixture. Once the methods are defined, you can run them. The framework supports both the static type safe and more dynamic way to run a test. In a static way, you override the run test method and define the method to be invoked. The convenient way to do is with an anonymous inner class. The dynamic way uses reflection to implement run test. It dynamically finds and involves a method. In this case, the name of the test case has to correspond to the test method to be run. The test to be run can be collected into a test suite. JUnit provides different test runners which can run a test suite and collect the results. A test runner either expects a static method suite as an entry point to get a test to run, or it can extract suite automatically. Assert not null method asserts that an object isn't null. Assert false asserts that an condition is false if it isn't throws throws an assertion failed error. Assert equals here. Assert that two objects are equal, here expected and actual here. If they are not, an assertion failed error is thrown. A JUnit test case extend the JUnit test API class test case, and each test method must start with the word test. To run the tests in Eclipse, right click on the test class in the package explorer view and choose run as JUnit test. As an example 3, we can consider this JUnit 4 test case. The annotation type test. The test annotation tells JUnit that the public void method to which it is attached can be run as a test case. To run the method, JUnit first construct a fresh instance of the class, then invokes the annotated method. Any exception thrown by the test will be reported by JUnit as a failure. If no exceptions are thrown, the test is assumed to have succeeded. In exception testing, the parameter expected declares a test method should throw an exception. If it doesn't throw an exception, or if it throws a different exception than the one declared, the test fails. Using the parameter expected for exception testing comes with some limitations. Only the exceptions type can be checked, and it is not possible to precisely specify the code that throws the exception. Therefore, JUnit 4 has improved its support for exception testing with assert.assertThrows class throwing runnable and the expected exception rule. With assert-throws, the code that throws the exception can be precisely specified. If an exception message or one of its properties should be verified, the expected exception rule can be used. Timeout. The parameter timeout causes the test to fail if it takes longer than a specified amount of clock time measured in milliseconds. Warning: while timeout is useful to catch and terminate infinite loops, it should not be considered deterministic. Thread safety warning: test methods with timeout parameter are run in a thread other than the thread which runs a fixture ampersand before and ampersand after methods. This may yield different behavior for code that is not thread safe when compared to the same test method without timeout parameter. Consider using timeout rule instead, which ensure the test method is run on the same thread as the fixtures ampersand before and ampersand after methods. To run to your JUnit 3 or 4 test as is on the JUnit platform, simply include JUnit vintage dependency in your build and it just works. The Maven POM and Gradle build file build.gradle that are included with the same application already do this. You can run test right out of the box. In JUnit 4, a JUnit 4 test case ends with the word test. Here it is omitted here, and each test method is annotated with ampersand test. To run this test in Eclipse, right click on the test class in the package explorer view and choose run as, then JUnit test. Assert not null. Asserts that an object isn't null if it is an assertion error. If it is If it is, and then an assertion error is thrown. Assert false method asserts that a condition is false. If it isn't, it throws an assertion error without a message. Assert equals asserts that two longs are equals. If they are not, an assert error is thrown. This is the expected long value, and this is the actual long value. As an example 4, we can consider this Gradle segment here. The JUnit platform can run JUnit 4-base test as long as you configure test implementation dependency on JUnit 4 and test and runtime only dependency on JUnit vintage-engine implementation, similar to following here. And here org.junit.vintage, this is the group ID. As an example 5, we can consider this Maven segment. Maven Surefire and Maven failsafe can run JUnit 4 based test alongside Jupyter test as long as you configure test scoped dependencies on JUnit 4 and JUnit vintage test engine implementation, similar to following. And here you can see JUnit vintage group ID. This is JUnit vintage here. As an exception example, we can consider this code segment. This is a test exception in JUnit 3. Here you can see the public string get message method. This returns the detailed message string of this throwable. Here assert equals asserts the two strings are equal here. It's expected and it's actual. As an exception, example 2, we can consider this one, test exception in JUnit 4. The class expected exception rules, the class expected exception, the expected exception rule allows you to verify that your code throws a specific exception. This is in package org.junit.rules in version JUnit 4. This is available from version 4.7. You have to add expected exception rule to your test. This is here. This doesn't affect your existing tests After specifying the type of the expected exception, your test is successful when such an exception is thrown, and it fails if a different or no exception is thrown. This rule does not perform any special magic to make an execution continue if the exception had not been thrown. If it is nearly always a mistake for a test method to have statement after the one that is expected to throw the exception. Instead of specifying the exception type, you can characterize the expected exception based on other criteria too. The exception message contains a specific test. Here expect message and a string. The exceptions message compiles with the hamcrest matcher, expect message matcher, or the exception cause compiles with the hamcrest matcher, expect cause matcher. The exception itself compiles with the hamcrest matcher, expect matcher. You can also combine any of the presented expect methods. The test is successful if the specifications are met. It is recommended to set order of the expected exception to integer.max value. If it is used together with another rule that handles the exception, for example error collector. Otherwise failing test may be successful. The assumption violated exceptions. JUnit uses assumption violated exceptions for indicating the test provide no useful information. You have to call assume method before you set expectations of the expected exception rule. In this case, the rule will not handle consume the exceptions, and it will handle by the framework. Now we are focusing on JUnit 4.12. As an example, we can consider this code segment. Here the annotation type test. The test annotation tells JUnit that the public void method to which it is attached can be run as a test case. To run the method, JUnit first construct a fresh instance of the class, then invokes the annotated method. Any exceptions thrown by the test will be reported by JUnit as a failure. If no exceptions are thrown, the test is assumed to have succeeded. This is in the package package org.junit. As an example 2, we can consider this Maven segment. Maven Surefire and Maven failsafe can run JUnit 4 based test alongside Jupyter tests, as long as you configure test scope dependencies on JUnit 4 and the JUnit vintage-engine implementation similar to following here. And you can see here JUnit 4 and the scope test. Test annotation supports two optional parameters for exception testing and for limiting test execution time. Here we are considering expected parameter for as an exception example here. The parameter expected declares that the test method should throw an exception. If it does not throw an exception, or if it throws a different exception than the one declared, the test fails. For example, this test succeeds here. Using the parameter expected for exception testing comes with some limitations. Only the exceptions type can be checked, and it is not possible to precisely specify the code that throws the exception. Therefore, JUnit 4 has improved its support for exception testing with assert throws class throwing runnable and the expected exception rule. With assert throws, the code that throws the exception can be precisely specified. If the exception's message or one of its properties should be verified, the expected exception rule can be used. As an error example, we can consider this one occurred in Android Studio. Failed to resolve JUnit 4.12. Now we are focusing on junit-vintage-engine. junit-vintage-test-engine implementation that allows one to run vintage JUnit test on the JUnit platform. Vintage test includes those written using JUnit 3 or JUnit 4 APIs, or test written using testing frameworks built on those APIs. Core package for the JUnit vintage test engine. Here you can see the dependency diagram. Here you can see JUnit vintage engine in org.junit.vintage package. As an example, we can consider the module org.junit.vintage.engine. Provides a test engine for running JUnit 3 and 4 based test on the platform. As an example 2, we can consider org.junit.vintage.engine package, core package for the JUnit vintage test engine. See, this is in module org.junit.vintage.engine. As an example 3, we can consider vintage test engine. The class vintage test engine, the JUnit vintage test engine. This is available since version 4.12, and this is in the module org.junit.vintage.engine, and in the package the org.junit.vintage.engine. As an example 4, we can consider this Gradle segment. The JUnit platform can run JUnit 4 based test as long as you configure test implementation dependency on JUnit 4 and test runtime only dependency on JUnit vintage test engine. Implementation similar to following, and here you can see artifact JUnit vintage engine. This is the module JUnit vintage engine of JUnit 5. This is in the group ID org.junit.vintage. As an example 5, we can consider this Maven segment. Maven Surefire and Maven failsafe can run JUnit 4 base test alongside Jupyter test as long as you configure test scope dependencies on JUnit 4 and the JUnit vintage test engine implementation similar to following here. And here you can see artifact JUnit artifact ID junit-vintage-engine here. The module junit-vintage-engine of JUnit 5 is in the group ID org.junit.vintage. As an exception example, we can consider this one internal record and org.junit.platform.commons.junit exception test engine with ID JUnit vintage failed to discover test, etc. As an error example, we can consider this java.lang.no such method error org.junit.vintage.engine.descriptor.runner test description get all descendants. As an error example 2, we can consider this error occurred in Spring Boot 2.2 and JUnit 5 environment. Failed to execute goal org.apache.maven.plugins.maven file sure plugin plugin 2.22.2 test default test on project xxx. There are test failures and etc. Then yeah, here please refer to the project workspace xxx target file. Surefire reports the individual test results. Please refer to the dump files if any exist. There was an error in the forked process. Test engine with ID JUnit vintage failed to discover test, etc. Now we are focusing on new test JUnit 5. New tests JUnit 5. As an example, we can consider this code segment. Here you can see annotation interface test. Test is used to signal that the annotated method is a test method, and at test method must not be private or static and must not return a value, and ampersand test methods may optionally declare parameters to be resolved by parameter resolvers. Ampersand test may also be used as a meta annotation in order to create a custom composed annotation that inherits the semantics of ampersand test. The annotation interface disabled here. Disabled is used to signal that the annotated test class or test method is currently disabled and should not be executed. Ampersand disabled may optionally be declared with a reason to document why the annotated test class or test method is disabled. This one, when applied at the class level, all test methods within that class are automatically disabled as well. When applied at the method level, the presence of this annotation does not prevent the test class from being instantiated. Rather, it prevents the execution of the test method and method level lifecycle callbacks such as ampersand before each method Assign after each methods and corresponding extension APIs. This is modify the reason this annotation test class or test method is disabled here. These annotations are in the module org.junit.jupiter.api and in the package org.junit.jupiter.api. As an exception example, we can consider this code segment here. Public static t extend throwable t assert throws class t executable. Assert that the execution of supplied executable throws an exception of the expected type and return the exception. If no exception is thrown, or if an exception of a different type is thrown, this method will fail. If you do not want to perform additional checks on the exception instance, ignore the return value. Here this is the expected type and this is the executable. Here here in assert equals assert that the expected and actual are equal. If both are null, they are considered equal. Here and this is the expected and this is the actual. These methods are in class assertions. As an error example, we can consider this code segment. This error occurred in the environment JUnit 5, Java 9 and Eclipse Oxygen 1.8. Java.lang.class no class def found error. Org junit-platform-launcher core launcher factory, then etc. Now we are focusing on Jupyter. JUnit-Jupyter is the combination of the new programming model and extension model for writing tests and extensions in JUnit 5. The Jupyter subproject provides a test engine for running Jupyter-based tests on the platform. Here in dependency diagram, you can see org.junit.jupyter package, and you can see here junit-jupiter-engine and junit-jupiter migration support, junit-jupiter params, and this is junit-jupiter, and here junit-jupiter-api. Here you can see per method lifecycle. With regarding lifecycle methods, a lifecycle method is any method that is annotated with before all, after all, before each, and or after each annotation. The lifecycle methods execute before or after executing the actual test methods. Before all and after all annotations denote that the annotated method should be executed before or after all test methods in the test class. If you have 10 test methods in the test class, before each and after each will be executed 10 times, but before each and after each here, but before all and after all only once. Here you can see a per method lifecycle. In per method lifecycle, this is a test instance lifecycle here. By default, JUnit creates a new instance of the test class before executing each test. Each test method. This helps us to run individual test methods in isolation and avoid unexpected side effects. Here, this before all and after all are static methods normally. This is because when creating a new test instance per test method, there is no shared state otherwise. When you're looking at the output, we can see that JUnit construct the test class once per each test. Each test method. The lifecycle methods for entire fixture have been executed once, and the lifecycle methods for tests have been executed multiple times. Here the annotation interface before all, emphasizing before all is used to signal that the annotated method should be executed before all tests in the current test class. In contrast to emphasizing before each methods, before all methods are only executed once for a given test class. Annotation interface before each, emphasizing before each is used to signal that the annotated method should be executed before each emphasizing test or repeated test, or emphasizing parameterized test, or emphasizing test factory, and emphasizing test template method in the current test class. Annotation interface after each, emphasizing after each is used to signal that the annotated method should be executed after each emphasizing test, emphasizing repeated test, emphasizing parameterized test, emphasizing test factory, and emphasizing test template method in the current test class. Annotation interface after all, emphasizing after all is used to signal that the annotated method should be executed after all tests in the current test class. In contrast to emphasizing after each methods, after all methods are only executed once for a given test class. Here, before all is connected to constructor test class instance, and constructor test class instance is connected to before each, emphasizing before each, and emphasizing before each is connected to execute test. Execute test is connected to emphasizing after each. After is connected to construct a test class instance. Next test is passed from after each to construct a test class instance. After each, emphasizing after is connected to emphasizing after all test done is passed from emphasizing after each to emphasizing after all. Here you can see test see a per class lifecycle or test instance per class. It is also possible to make JUnit execute all test method in the same test instance. if we annotate the test class with ampersand test instance lifecycle.per-class, JUnit will create a new test instance once per test class. So because of the shared instance, there is now no need for the method to be static. From the execution results, we can see that the execution order of the lifecycle methods has not changed. However, the difference is that JUnit constructs the test class only once. The fundamental difference is that the default lifecycle method constructing a new test class instance resets the state stored in the instance variable. When per class lifecycle method construct the instance only once, state stored in instance variable is shared between tests. If your test methods rely on state stored in instance variable, you may need to reset the state in before each and or after each lifecycle methods. Try to avoid writing tests that rely on state stored in instance variables. Here you can see the construct a test class instance is connected to assign before all, and before is connected to before each, and before each is connected to execute test, and execute test is connected to after each, after is connected to before each, and new test is passed from after each to before each, and after is connected to after all, and all test done is passed from after each to after all. Here you can see extension lifecycle. junit-Jupiter provides extension authors callbacks that can be used to tap into the lifecycle events of tests. The extension model provides several interfaces for extending test at various points in the extension lifecycle. Extension authors are free to implement all or some of these lifecycle interfaces. Interface before all callback. Before all callback defines the API for extensions that wish to provide additional behavior to test containers once before all tests in the container have been executed. Interface before each callback. Before each callback defines the API for extensions that wish to provide additional behavior to test before an individual test and any user-defined setup methods. For example, ampersand before each methods. For that, the tests have been executed. Interface before test execution callback. Before test execution callback defines the API for extensions that wish to provide additional behavior to test immediately before an individual test is executed, but after any user-defined setup methods. For example, ampersand before each methods have been executed for that test. Interface after test execution callback. After test execution callback defines the API for extensions that wish to provide additional behavior to test immediately after an individual test has been executed, but before any user-defined teardown methods. For example, ampersand after each methods have been executed for that tests. Interface after each callback. After each callback defines the API for extensions that wish to provide additional behavior to tests after an individual test and any user-defined teardown methods. Ampersand after each methods for that test have been executed. Interface after all callback. After all callbacks defines the API for extensions that wish to provide additional behavior to test containers once after all tests in the container has been executed. Here you can see the lifecycle callbacks here. Before all callback is connected to before each callbacks, and before each callbacks is connected to before test execution callback. Before test execution callback is connected to after test execution callback. After test execution callback is connected to after each callback. After each callback is connected to after all callback. As an example, we can consider JUnit-jupiter-params. The artifact ID JUnit-jupiter-params. Support for parameterized tests in JUnit-jupiter. This is in the group ID org.junit.jupiter. As an example 2, we can consider this code segment. Following example demonstrates a parameterized test that uses ampersand value source annotation to specify a string array as the source of arguments. Annotation interface parameterized test. Ampersand parameterized test is used to signal that the annotated method is parameterized test method. Such methods must not be private or static. Parameterized tests make it possible to run a test multiple times with different arguments. They are declared just like a regular ampersand test method, but use ampersand parameterized test annotation instead. In addition, you must declare at least one source that will provide the argument for each invocation, and then consume the arguments in the test method. When executing this parameterized test method, each invocation will be reported separately. For instance, the console launcher will print output similar to the following here. As an example 3, we can consider JUnit artifact ID JUnit-jupiter-migration support. Support for migrating from JUnit 4 to JUnit Jupiter, only required for support for JUnit 4's ampersand ignore annotation and for running selected JUnit 4 rules. This is in group ID org.junit.jupiter. Here, as an example 4, we can consider this code segment. Annotation interface enable JUnit 4 migration support. Enable JUnit 4 migration support is a class level annotation that enables all JUnit 4 migration support within JUnit Jupiter. Specifically, this annotation registers all extensions supported by ampersand enable rule management rule migration support, and provides support for JUnit's force ampersand ignore annotation for disabling test classes and test methods. Technically speaking, ampersand enable JUnit for migration support is a composed annotation which registers all of the following migration extensions: verifier support, external resource support, expected exception support, and ignore condition. Note, however, that you can optionally register one or more of these extensions explicitly without the use of this composed annotation. And this is in module org.junit.jupiter.migration support, and in the package org.junit.jupiter.migration support. In order to provide the smooth migration path from JUnit 4 to JUnit Jupiter, the JUnit-jupiter-migration support module provides support for JUnit 4's ignore annotation analogous to Jupyter's disabled annotation. To use ignore with JUnit Jupiter based test, configure a test dependency on the JUnit-jupiter-migration support module in your build, and then annotate your test class with extent with ignore condition.class, or enable enable JUnit for migration support, which automatically registers the ignore condition along with limited JUnit for rule support. The ignore condition is an execution condition that disable test class or test methods that are annotated with the ignore. As an example 5, we can consider this Gradle segment. To configure support for JUnit Jupiter based test, configure a test implementation dependency on the dependency aggregating JUnit Jupiter artifact, similar to the following here. And here you can see the group ID org.junit.jupiter, JUnit Jupiter here. As an example 6, we can consider this one, the Maven segment here. To configure the support for JUnit Jupiter based tests, configure test scoped dependencies on the JUnit Jupiter API and the JUnit Jupiter test engine. Implementation similar to following here. You can see the here group ID org.junit.jupiter, JUnit Jupiter here. Here, as an example 7, we can consider per method lifecycle here in this code segment. A lifecycle method is we are considering lifecycle methods also. A lifecycle method is any method that is annotated with sign before all, sign before after all, sign before each, sign after each annotation. Lifecycle methods execute before or after executing the actual test methods. The ampersand before all and ampersand after all annotations denote that the annotated method should be executed before or after all test methods in the test class. Respectively, ampersand before each and ampersand after each means that annotated method should be executed before and after each test method in the test class. if you have 10 methods, 10 test methods in the test class, before each and after each will be executed 10 times, but before all and after all only once. By default, JUnit creates an per method lifecycle. By default, JUnit creates a new instance of the test class before executing each test. This helps us to run individual test methods in isolation and avoids unexpected side effects. Notice how the methods annotated with ampersand before all, ampersand after all are static methods. This is because when creating a new test instance per test method, there is no shared state otherwise. Executing the test in the test class gives us the following output. Actually, the output has been formatted to make it more obvious. Looking at the output, we can see that JUnit constructs the test class once per each test. Test method, the lifecycle method for an entire fixture has been executed once. And the lifecycle method for test have been executed multiple times. Here, annotation interface before all. Ampersand before all is used to signal that the annotated method should be executed before all tests in the current test class. In contrast to ampersand before each methods, ampersand before all methods are only executed once for a given test class. Annotation interface after all. Ampersand after all is used to signal that the annotated method should be executed after all tests in the current test class. In contrast to ampersand after each methods, after all methods are only executed once for a given test class. Annotation interface before each. Ampersand before each is used to signal that the annotated method should be executed before each ampersand test, repeated test, ampersand parameterized test, ampersand factory, and ampersand test template methods in the current test class. Annotation interface after each is used to signal that the annotated method should be executed after each ampersand test, repeated test, ampersand parameterized test, ampersand test factory, and ampersand test template method in the current test class. Here the ampersand test is used to signal that annotated method is a test method, and ampersand test methods must not be private or static, and must not return a value. Ampersand test method may optionally declare parameters to be resolved by parameter solvers, and ampersand test may also be used as a meta annotation in order to create custom composed annotation that inherits the semantics of ampersand test. Per class lifecycle, it is also possible to make JUnit to execute all test methods on the same test instance. If we annotate the test class with ampersand and its test instance lifecycle.per_class, JUnit will create a new test instance once per test class. Because of the shared instance, there's now no need for the methods to be static. Consequently, output of the test execution is now a little different. From the result, we can see that the execution order of lifecycle methods has not changed. However, the difference is that the JUnit construct a test class only once. The fundamental difference is that the default lifecycle method constructing a new test class instance and reset the state stored in the instance variable. When the per class lifecycle method construct the instance only once, state stored in the instance variables is shared between tests. If your test methods rely on the state stored in instance variable, you may need to reset the state in ampersand before each and ampersand after each lifecycle methods. Try to avoid writing tests that rely on state stored in instance variables. Extension lifecycle. When using extensions, JUnit calls extension lifecycle callbacks in addition to lifecycle methods in the test class. JUnit guarantees wrapping behavior for multiple registered extensions. Given extension 1 and extension 2, it is guaranteed the before callbacks of extension 1 execute before extension 2. Similarly, it's guaranteed by after callbacks of extension 1 execute after extension 2. Executing the example here, we can see the wrapping behavior of the extensions. Interface before each callback. Before each callback defines the API for extensions that wish to provide additional behavior to test before an individual test, and any user-defined setup methods. For example, before before each methods for that test have been executed. Concrete implementation often implement after each callback as well. If you do not wish to have your callback wrapped around user-defined setup and teardown methods, implement before test execution callback and after test execution callback instead of before each callback and after each callback. Here you can see the method void before each extension context and this callback that is invoked before an individual test and any user-defined setup methods for that test have been executed. Interface after each callback. After each callback defines API for extensions that wish to provide additional behavior to test after an individual tests and any user-defined teardown methods, for example, after each for that test have been executed. Concrete implementation often implement before callback as well. If you do not wish to have your callback wrapped around user-defined setup and teardown method, implement before test execution callback and after test execution callback instead of before each callback and after each callback. Method void after each extension context callback that is invoked after an individual test and any user-defined teardown methods for that the test have been executed. Here annotation interface extend with. Ampersand extend with is a repeatable annotation that is used for to register extension for the annotated test class, test interface, test method, parameter field. Annotated parameters are supported in test class constructed in test methods and in ampersand before all, ampersand after all, ampersand before each, ampersand after each cycle methods. Ampersand extend with fields may be either static or non-static. As an error example, we can consider this one. Ampersand parameter 0 is used more than once, and java.line.exception parameter is used more than once at org.junit.runners.parameterize.block junit for test class runner with parameters.valid text field. Now we are focusing on junit-jupiter-api. junit-jupiter-api for writing tests and extensions. As an example, we can consider the module org.junit.jupiter.api defines junit-jupiter-api for writing tests. As an example too, we can consider this code segment writing tests. The following example provide a glimpse at the minimum requirement for writing a test in junit-jupiter. Annotation interface test. Ampersand test is used to signal that the annotated method is a test method. Annotation method must not be private or static and must not return a value. Annotation test methods may optionally declare parameters to be resolved by parameter resolvers, and annotation test may be used as a meta annotation in order to create a custom composed annotation that inherits the semantics of ampersand test. This is in the module org.junit.jupiter.api and package org.junit.jupiter.api. As an example 3, we can consider extension model. For example, to register a web service extension for a particular test method, you would annotate the test method as follows here. We assume the web server extension starts a local web server and injects the server's URL into parameters annotated with ampersand web server URL. Annotation interface extend with. Ampersand extend with is a repeatable annotation that is used to register extension for the annotated test class, test interface, test method, parameter or field. Here you can use web client to connect to web server and verify response. Here assert equals assert that expected and actuals are equal. This is expected and this is actual. As an example 4, we can consider this Gradle example. Here you can see the artifact ID JUnit-jupiter-api. This is in the group org.junit.jupiter. As an example 5, we can consider this Maven segment. You can see the artifact ID JUnit-jupiter-api here. This is in the group org.junit.jupiter. Here the version 5.8.2 and scope is test. As an example, we can consider this code segment. Here the method public static t extend throwable t assert throws class t expected value an executable here. Assert that execution of the supplied executable throws an exception of the expected type and returns the exception. If no exception is thrown, or if the exception is of a different type is thrown, this method will fail. If you do not want to perform additional checks on the exception instance, ignore the return value. This method is in class assertions. As an error example, we can consider this error occurred in the environment JUnit and Maven project. This error occurred in JUnit and Maven project in NetBeans. Error package org.junit-jupiter-api does not exist. Now we are focusing on junit-jupiter-engine. JUnit-Jupiter-test-engine implementation only required at runtime. As an example, we can consider package org.junit.jupiter.engine, core package for the JUnit-Jupiter-test-engine is in module org.junit.jupiter.engine. As an example 2, we can consider default Jupyter configuration class, default implementation of the Jupyter configuration API. This is in the module org.junit.jupiter.engine and package org.junit.jupiter.engine.config. As an example 3, we can consider this code segment. Here you can see the class Jupyter test engine, the JUnit Jupyter test engine. Here you can see the method public test description discover here, engine discovery request and unique ID here. This method discovers test according to the supplied engine discovery request. This class is in module org.junit.jupiter.engine and package the org.junit.jupiter.engine. Here the supplied unique ID must be used as the unique ID of the returned root test descriptor. Here the engine discovery request provide the test engine access to the information necessary to discover test and containers. And the unique ID encapsulates the creation and passing and display unique IDs for test descriptors. The interface test descriptor, the mutable descriptor for a test or container that has been discovered by a test engine. Here you can see the Gradle segment for additional Gradle dependencies for IntelliJ IDEA. Here you can see artifact ID JUnit-Jupiter-engine, module JUnit-Jupiter-engine of JUnit 5, JUnit-Jupiter-test-engine implementation only required at runtime here. This is in the group ID org.junit.jupiter. You can see this one, JUnit-Jupiter-engine. As an example 5, we can consider this Maven segment for additional Gradle dependencies for IntelliJ IDEA. Here you can see artifact ID junit-jupiter-engine, module junit-jupiter-engine of JUnit 5, junit-jupiter-test-engine implementation, only required at runtime. This is in the group ID org.junit.jupiter. As an exception example, we can consider test execution exception handler, interface test execution exception handler. This is a functional interface and can therefore be used as the assignment target for a lambda expression or method reference. This is in the package org.junit.jupiter.api.extension. Now we are focusing on other tests. As an example, we can consider this code segment. Here 3 test cases for a new engine. This following example annotates the test class with the ampersand web smoke test. To identify the test classes, it contains 3 separate test cases. Identified by simple field, and each field is annotated with ampersand get, denoting the need to execute an HTTP get request. Supporting post or other HTTP verbs would be just as simple. The target URL. The target URL of the request is specified in the value of the field. As mentioned usually you have complete freedom in the new test engine regarding how to design a test model. You might have used method as most traditional test engine do, or you might have specified the expected value as a method return type. All are perfectly valid options. Here you can see the execution of the main engine class in the IDE. Here you can, as an example, you can see here you can see the execution of the main engine class in the IDE. As can be seen in this figure, the project, the specific project here uses domain-specific custom display names to reference to the individual test cases in the GUI of the execution IDE. Thus, in this case, you can even display the whole test definition, the URL, and the expected status code right next to the IDE symbol indicating success or failure. Such flexibility is enabled by the descriptor module, referring the freeing the IDE from the need to mechanically display plain method or field names in all cases. Here you can see the failure here. Now we are focusing on third party. As an exception example, we can consider this. If any third-party test engine claims to be JUnit-Jupiter or JUnit-vintage, an exception will be thrown immediately, halting execution of the JUnit platform. As an error example, we can consider this occurred in the environment with Java 8. Here, warning third-party test engine implementations are forbidden to use the reserved JUnit prefix for their ID JUnit platform suite. Then org.junit-platform-launcher.core.default launcher handle throwable, etc. Now we are focusing on custom API. Here you can see the execution of a single test. The execute test method is responsible for sandwiching the actual execution call between lifecycle events. The execute text field method retrieve the URL and the expected status code and then actually execute HTTP request via a purely technical helper method. If a response is received, the method checks the actual status code and creates a test execution result dot failed result failed with an assertion failed error in case the response does not meet the expectation. If sending the request throws an exception, it is wrapped in a more technical runtime exception and text execution result and test execution result dot failed result. If all goes well, the method returns a text execution result successful result. This basically is the complete custom test engine. Now we are focusing on custom engine. Here you can see a JUnit 5 platform architecture. Contrary to the public opinion, JUnit 5 is a platform rather than simple test runner. To understand the need for such platform, it is helpful to take a look at some JUnit history. Early versions of JUnit were not designed with tool integration in mind. Due to wild success of these early versions, however, IDEs and build tools began integrating JUnit into their environments quite soon. However, because JUnit was not designed to be executed from third-party process, integrators sometimes had to rely on dangerous mechanisms such as reflection to make things work. In such integrations were naturally brittle and were very hard to change and maintain because the outside world relied upon and was coupled to JUnit's internals, even private members. In an infamous example for this coupling is the breaking of the integration in widely used IDE when a JUnit 4.x version changed the name of the private field. The situation was only exacerbated by other test libraries and frameworks mimicking JUnit structure to leverage JUnit's IDE integration. Therefore, while planning and designing the new generation of JUnit, and the JUnit team took special care to avoid coupling. As a matter of fact, the team invited representative from their major IDEs and build tools to kick off meeting in October 2015 to discuss a solid foundation for integration architecture. The main goal was to provide a different API for different groups of users, namely an engine service provider interface (SPI), JUnit platform-engine for integrators of existing test engines and authors of new test engines, or a launcher API, junit-platform-launcher for IDEs and build tools to provide stable and transparent means of integrating all test engines. An annotated based API, junit-jupiter-api for test authors, which would be similar in look and feel to JUnit 4X generation, but with the more flexible extension model. The first two are the core component of JUnit 5 platform, and this figure shows the essential parts of the JUnit 5 platform and several engines built upon it. This clear separation of concerns is fundamental to the new architecture and has so far served well to avoid problematic coupling. As a consequence, the JUnit platform has been integrated into all major IDEs and build tools using Launcher API. Similarly, the platform-engine SPI has been used to integrate various test engines with the JUnit 5 platform. This allows the test engine authors to concentrate on the test definition and execution concerns and completely disregard the aspects of launching their test cases from IDEs and build tools. A special case is, of course, JUnit's own Jupyter test engine, which uses a new JUnit 5 test model. However, even this built-in engine uses only the public API and has no secret access to other parts of JUnit 5. To show how easy it is for engine authors to integrate tools with the JUnit platform, for example, you will develop a very small test engine from scratch, and we name it as WebSmoke here. Here, test engines WebSmoke, JQ, Wick, and junit-jupiter are in test engines, and WebSmoke and JQ and junit-jupiter are connected to junit-platform-engine SPI. SPI, junit-platform-engine, and API, junit-platform-launcher are in junit-platform. API, junit-platform-launcher is connected to junit-platform-engine. Tool IDE, build tools are in third-party tooling, and tool IDE and tool build tools are connected to API junit-platform-launcher. Here you can see an implementation of a custom test engine. Interface test engine. Test engine facilitates discovery and execution of tests for a particular programming model. For example, JUnit provides a test engine that discovers and executes tests written using JUnit-Jupiter programming model. Every test engine must provide its own unique ID. Discover tests from engine discovery requests. And execute those tests according to execution requests. In order to facilitate test discovery within IDEs and tools prior to launching the JUnit platform, test engine implementations are encouraged to make use of ampersand testable annotation. For example, the ampersand text and ampersand test factory annotations in junit-jupiter are meta annotated with ampersand testable. From most JVM languages, being the test model on classes and methods seems a natural fit. However, other test definition models, in principle, as long as individual tests can be described unambiguously by an org.junit.platform.engine.test description implementation. Typically, a test description implementation has to be provided by a test engine author and represent a testable element of the given programming model, such as a single test, field test descriptor, or container of test class test descriptor. For the purpose of this example, we want to implement an engine that is both small and lightweight. Hence, we could contemplate alternatives to a method-based test model. One option might be to use lambdas assigned to fields, because lambdas can be considered a form of lightweight methods. This is possible since we could use java.util.function.predicate implementation using aptly named method boolean test tt for test execution and boolean as a success or failure indicator. While such lambdas might be a bit more lightweight than full-blown method, maybe we can take a bit further. As mentioned before, there can be different reasons for creating custom engine. Here you want to support the requirement of a special domain in such way that creating tests becomes very simple for test author. As a simple yet still useful example, we pick the domain HTTP based mock tests. In this case, the test that merely test whether a URL works. Specifically, you need a succinct way to define the URL against which the mock test would be executed. A simple means to specify expected HTTP status code. Consider the test successful if the GET request against the specified URL result in the specified HTTP status code. As for the behavior, the degrees of freedom are extremely limited. A mock test always does the same thing, namely and execute HTTP requests against a certain Since this test does not need variants in behavior, you can get rid of methods will explicitly program statement entirely, or lambdas for that matter. You can choose completely declarative approach. When you design a custom test engine, it is important to understand the contract between a test engine and a JUnit platform. This contract is defined by org.junit-platform-engine.testengine. Interface would look here. String get ID, test descriptor discover, engine discovery request, unique ID, and execute, void execute, execution request. Apart from some optional metadata, this interface contains the three core responsibilities of a test engine. These core responsibilities are identification. The engine must provide a unique string by which it can be referenced and differentiated from other engines on the class path. For example, Jupyter's ID is JUnit-Jupiter. Discovery. Engine must be able to inform the JUnit platform about everything it considers its own test cases. These are arranged in a tree structure with the return test descriptor. Execution: when requested by the platform, the engine must be able to execute a given execution request. This request contains a test descriptor referencing the test to be run and provides the engine execution listener to the engine. The former previously returns the engine's own discover method. The latter is used by the engine implementation to fire test lifecycle events such as execution started, execution finished. In many cases, test engines will support a hierarchical test definition model mirroring Java's hierarchical structure of packages, classes, and methods. The JUnit platform provides special support for such hierarchical engine in the form of the org.junit.platform.engine.support.hierarchical test base class. JUnit's own Jupyter test engine is itself an extension of this base class. By using this support, advanced features such as parallel execution can be readily reused by the custom engines. However, for the sake of simplicity and clarity, WebSmoke test will not use this base class. It will implement the required interfaces directly. Implementing the minimum test engine here. A test engine usually consists of the engine class itself and one or more test description implementations. This is in no way mandatory. And in this example here there are two annotations. This is no mandatory when designing this exercise here. We happen to choose an annotation based testing model. For such implementation, JUnit platform provides good support with the org.junit.platform.commons.support.annotation support utility. Here that you can see the integration, discovery, and execution work. The discover engine discovery request, unique ID methods creates an engine descriptor and add test descriptions hierarchically, while engine discover request gives access to the several implementation of org.junit.platform.engine.discovery selector. Such selectors can be reference various structural elements in Java such as method, classes, packages, and whole class path or the file system, file directories, as well as JUnit's own unique ID instances. Basically, the such selectors can reference various structural element of Java such as method, such as methods, classes, packages, and whole class path. or the file system, files, directories, as well as JUnit's own unique ID instances. The test engine uses these to indicate to the requesting tool, such as IDE, what it considers test cases associated with every such element according to a specific test model. The last method here takes care of test execution. Execute execution request, accept an execution request, and delegates most of his actual work to a helper class named smoke text executor. In this class, the various test descriptor variants are handled and individual tests are executed. As an example too, we can consider this the JUnit configuration file using the Java SPI mechanism. Test engine integration. This test engine class can be immediately executed in an ID such as IntelliJ IDEA if two conditions are fulfilled. First, you need to test engine code on the class path, typically in a Maven or Gradle dependency. Second, the new engine must be registered with the JUnit platform. This is done via Java's well-known SPI. To this end, the special file must be present in the class path, as you can see in this figure. For the SPI mechanism to work, the file name must specify the SPI. Here names the org.junit-platform-engine.testengine. The file contains only one line, the fully qualified name of the main engine class, which in this case is the org.example.websmoke.engine.websmoke-testengine. This FQN must refer to a class implement in the interface specified by the file name. When the main engine class is executed in the IDE, the test result should display. As an example 3, we can consider this one using test engine test kit. Using engine test kit, a simple integration test for your custom test engine look as follows. You made a good progress with the implementation of a new custom test engine now, and you also try it out by running some example test in that IDE. Everything seemed to work, but however, as a professional developer, you would like to have a more rigorous approach to validate the new test engine. You may also want a way of running systematic and automatized test of the engine. After all, this is the key paradigm of any form of test-centered development. First approach might be to use a new test engine to test itself. While this can add some extra assurance, it does not suffice, because if you use test engine to test itself, you might fall for error masking. That's when you might not find a bug in the implementation, because another buggy part of the engine hides that failure. In addition to that, the example test engine is a domain specific tool for a web smoke testing, and it is thus not capable of asserting the general correctness of software. Enter engine test kit, or more specifically the module junit-platform-test kit, is a special integration testing tool provided by JUnit Platform. Engine test kit is intended to test the interplay between JUnit Platform and the custom engine implementations. The class org.junit.platform.testkit.engine test kit provides an entry point to a Fluent API exposing test event. This offers a fine-grained assertion possibilities for comparing expected lifecycle events to actual ones. Using the example begins by proclaiming interest in your custom test engine, referenced by its engine ID, which is websmoke-test. Next, you can use one of many org.junit.platform.engine.discovery select implementations to narrow the scope down to the example class from here. Example web smoke test. Next, execute the selected test much in the same way an IDE would. This give you an access and org.junit.platform.testkit.engine.events instance upon which various checks can be performed. In this example, engine test kit checks the 3 tests were executed, 2 of which were completed successfully, and 1 that reported the failure. This is what you should expect. You should have expected here. You can use so that the custom web smoke test can be run in an IDE just like standard JUnit Jupyter tests. One interesting feature of the JUnit platform is the ability to execute different test engines in a single run. In the past, IDEs could implement such combined execution on their own, but the JUnit platform allows this consistency for all environments that connected via junit-platform-launcher. To demonstrate this, add the simple JUnit Jupyter test and have it execute together with the custom test engine tests. Here the class engine test kit. Engine test kit provides the support for executing a test plan for a given test engine and then accessing the result via a Fluent API to verify the expected result. Here the engine create an execution of engine test kit.build for the test engine with the supplied ID. The test engine will be loaded via this Java service loader mechanism analogous to the manner in which test engines are loaded in the JUnit platform-launcher API. Here select the method selectors, add all the supplied discovery selectors. The method execute tests for the configured test engine, discovery selectors, discovery filters, and configuration parameters, and returns recorded test engine execution results. The method events or test events, get recorded events for the test. In this context, word test applies to test descriptors that run the true from test descriptor.isTest method. Assert statistics for the events contained in this events object. Started, specify the number of expected started events. Succeeded, specify the number of expected succeeded event. Failed, specify the number of failed events. The example here, the example test class has 3 test cases and 2 successes and 1 failure. As an example 4, to demonstrate that this in IDE tests for different test engines are shown in a single graphical test execution 3 in the IDE. To demonstrate this combined execution is also portable over execution environments. You can start the standalone JUnit console runner with options like following. Here the console launcher options -e or dash include engine provide ID of an engine to be included in the test run. This option can be repeated. As a result, you get a nicely colored console output here. As another example, we can consider this one, execution of the main engine class in the IDE, and you can see here the fail test is in the environment IntelliJ IDEA. Now we are focusing on platform. The JUnit platform serves as a foundation for launching testing frameworks on the JVM. It also defines the test engine API for developing testing framework that runs on the platform. Furthermore, the platform provides a console launcher to launch the platform from the command line, and the JUnit platform suite engine for running a custom test suit using one or more test engines on the platform. First class support for the JUnit platform also exists in the popular IDEs. See IntelliJ IDEA, Eclipse, NetBeans, and Visual Studio Code, and build tools. Check like Gradle, Maven, and Ant. Here you can see a dependency diagram. In org.junit.platform, you can see JUnit platform test kit, JUnit platform suite, JUnit platform suite engine, JUnit platform suite commands, JUnit platform suite API, JUnit platform-runner, JUnit platform-JFR, JUnit platform-launcher, JUnit platform-console, JUnit platform reporting, JUnit platform-engine, JUnit platform commands. As an Maven example, we can consider this segment. Here you can see group ID org.junit.platform, JUnit platform. As a Gradle example, we can consider this one. IntelliJ IDEA supports here IntelliJ IDEA Gradle additional Gradle dependencies. IntelliJ IDEA supports running tests on the JUnit platforms since version 2016.2. Or not, however, that it is recommended to use IDEA 2017.3 or newer, since newer versions of IDEA will download the following jars automatically based on the API version used in the project: JUnit Platform-Launcher, junit-jupiter-engine, and junit-vintage-engine. IntelliJ IDEA releases prior to IDEA 2017.3 bundle specific versions of JUnit 5. Thus, if you want to use a newer version of junit-jupiter, execution of the test within the IDE might fail due to version conflict. In such cases, please follow this. In order to use different JUnit 5 version, for example 5.9.0, you may need to include corresponding versions of JUnit Platform-Launcher, junit-jupiter-engine, and junit-vintage-engine jars in the class path. Here you can see the group ID org.junit.platform in JUnit platform. Here you can see artifact ID as an example. We can consider as artifact ID JUnit platform console is standalone, an executable jar with all dependencies included is provided in Maven Central under JUnit platform console standalone directory. This is under group ID org.junit.platform. As an example 4, we can consider artifact ID JUnit platform JFR provides a launcher discovery listener and text test execution listener for Java flight recorder events on the JUnit platform. This is in the group org.junit.platform. As an example 5, we can consider JUnit platform reporting artifact, test execution listener implementations that generate test reports typically used by IDEs and build tools. This is in group ID org.junit.platform. As an example 6, we can consider artifact ID JUnit platform suite. JUnit platform suite artifact that transitively pulls in dependencies on junit-platform-surefire-API and junit-platform-surefire-engine for simplified dependency management in build tools such as Gradle and Maven. This is in the group ID org.junit.platform. As an example 7, we can consider artifact ID junit-platform-surefire-API. Annotations for configuring test suites on the JUnit platform. This is in group ID org.junit.platform. As an example 8, we can consider JUnit platform suite commons artifact. JUnit platform suite commons support is common support utilities for executing test suites on the JUnit platform. This is in group ID under the group ID org.junit.platform. As an example 9, we can consider artifact ID junit-platform-surefire-engine, engine that executes test suites on the JUnit platform only required at runtime. This is in the group ID org.junit.platform. As an example 10, we can consider artifact ID JUnit platform test kit. Provides support for executing a test plan for a given test engine and then accessing the results via a Fluent API to verify the expected results. This is in group ID org.junit.platform. As an exception example, we can consider JUnit exception, class JUnit exception, base class for all runtime exceptions thrown by JUnit. This is in the package org.junit.platform.commons. Now we are focusing on JUnit platform-engine, public API for test engines. As an Maven example, we can consider this segment. Here you can see artifact ID JUnit platform-engine. As an example, we can consider package org.junit.platform.engine, public API for test engines. This is in the module org.junit.platform.engine. Engine. And also the module org.junit.platform.engine also public APIs for test engines, provides the test engine interface, test discovery, and execution reporting support. As an example 3, we can consider suite test engine, class suite test engine, the JUnit platform suite test engine. This is in the module org.junit.platform.suite.engine and in the package org.junit.platform.suite.engine. As an example, example 4, we can consider registering test engine. For example, junit-jupiter-engine module registers its org.junit.jupiter.engine.jupiter test engine in a file named org.junit.platform.engine.test-engine within the /meta-inf/services folder in the JUnit-jupiter-engine jar. Test engine registration is supported via Java's service loader mechanism. The following example shows how to use org.junit.platform.engine.test engine. Interface test engine. A test engine facilitates discovery and execution of test for a particular programming model. Test engine registration is supported via Java service loader mechanism. This test engine is in module org.junit.platform.engine and package org.junit.platform.engine. Class service loader, a facility to load implementations of a service. Public static service loader load and class loader. Create a new service loader for the given service type and class loader. The service loader class is in module java.base and in package java.util. Here you can see a can be loaded cost in the JVM, and this is in the test class loader, but not available to the class loader. As an example 6, we can consider this. Here the interface configuration parameters that test engines may use to influence test discovery and execution. For example, junit-jupiter-engine uses a configuration parameter to enable IDE and build tools to deactivate conditional test execution. And optional boolean get boolean string key, get the boolean configuration parameter stored under the specified key. This is in module org.junit.platform.engine and package org.junit.platform.engine. As an exception example occurred in as an example, we can consider this code segment, this error information, exception information in the environment JUnit 5 with Eclipse, Java lang no class def found error, etc., and caused by Java lang class not found exception, org.junit.platform.engine.configuration parameters at java.base jdk internal loader built-in class loader load class built-in class loader.java, etc. As an error example, we can consider this exception in thread main java.lang.bootstrap method error, etc., and then caused by java.lang.no such method error, org.junit.platform.engine.testDescription.prune we add, etc. Now we are focusing on junit-platform-launcher, junit-platform-launcher, public API for configuring and launching test plans, typically used by IDEs and build tools. Here you can see the artifact ID platform junit-platform-launcher. This is in group ID org.junit.platform. As an additional Gradle dependencies for IntelliJ IDEA, we can consider this code segment as example 2 with the Gradle. You can see the artifact ID JUnit-platform-launcher here. This is in the group ID org.junit.platform. As an example 3, we can consider org.junit.platform.launcher module, public API for configuring and launching test plans. As an example 4, we can consider this code segment regarding discovering tests. Here interface launcher. The launcher API is the main entry point for client code that wishes to discover and execute tests using one or more test engines. Here the test plan discover, launch, discovery request, discover tests and build a test plan according to the supplied launcher the discovery request by querying all the registered engines and collecting their results. This is in module org.junit.platform-launcher and package org.junit.platform.launcher. Having test discovery as a dedicated feature of the platform itself frees IDE and build tools from most of the difficulties they had to go through to identify the test classes and test methods in previous versions of JUnit. You can select classes, methods and all classes in a package, or even search for all tests in a class path or module path. Discovery takes place across all participating test engines. The resulting test plan is a hierarchical and read-only description of all engines, classes and test methods that fit the launcher discovery request. The client can reverse the tree, retrieve details about a node and get a link to that original source like class, method or file position. Every node in the test plan has a unique ID that can be used to invoke particular test or group of tests. Clients can register one or more launcher discovery listeners, implement listener implementations via the launcher discovery request builder to gain insight into events that occur during the test discovery. By default, the builder registers an abort on failure listener that aborts test discovery after first discovery failure encountered. The default launcher discovery listener can be changed via junit.platform.discovery-listener discovery.listener.default configuration parameter. Here the launcher discovery builder provides a lightweight DSL for generating a launcher discovery request. Here the request create a new launcher discovery request builder. Here the method selectors add all the supplied selectors to the request. Here select package, the static method create package selector for supplied package name. Here select class, method create class selector for the supplied class. Here the filters method add all the supplied filters to the request. And here the build the launcher discovery request that has been configured via the builder, via this builder. Launcher session. Here launcher factory a factory for creating launcher instances by invoking create launcher config. Here open session method, public static launcher session open session method, factory method for opening a new launcher session using the default launcher config. Interface launcher session here. The launcher session API is the main entry point for client's code that wishes to repeatedly discover and execute tests using one or more test engines. Here launcher get launcher get the launcher associated with this session. And here discover additional test plans or execute tests. Here you can see executing test as example 5 here. Here here void execute launcher discovery request, then execute listeners. This method execute test execute a test plan which is built according to the supplied launcher discovery request. By queuing all the registered engines and collecting their results. And here execute test plan, then text execution listeners, execute the supplied test plan, and notify registered listeners about the progress and results the execution. To execute test, client can use the same launcher discovery request. Test progress and reporting can be achieved by registering one or more test execution listeners. Listener implementation with the launcher as in this example here. There's no return value for the execute method, but you can use text execution listener to aggregate the results. Here the summary generating listener, a simple text execution listener that generates a summary of the test execution. Here a register test execution listener method register one or more listeners for the text execution. Here the launcher here the test plan discover launcher discovery request method discover test and build a test plan according to the supplied launcher discovery request by querying all registers engines and collecting their results. Here text execution summary, get summary, get the summary generated by the listener, and here text the class the interface text execution summary is a summary of the test plan execution. Here register a listener for your choice. Here discover, test and build test plan. Here execute test plan, and alternate to execute the request directly. Here the test plan describes the class test plan. Here the describes the tree of tests and containers as discovered by a launcher. As an example 6, we can consider this one, registering a test engine. For example, junit-jupiter-engine module registers it junit-jupiter-engine.jupyter-test-engine in a file name org.junit.platform-engine.test-engine within the /meta-info/services folder in the junit-jupiter-engine jar. Test engine registration is supported via Java's service loader mechanism. As an example 7, we can consider registering a post discovery filter. For example, an example.custom tag filter class implementing post discovery filter and declared within /meta -inf/services org.junit.platform-launcher.post discovery filter file is loaded and applied automatically. Interface post discovery filter. Post discovery filter is applied to test descriptors after test discovery. In addition to specifying post discovery filters as part of launcher discovery request passed to the launch API, post discovery filter implementations will be covered at runtime via Java's service loader mechanism and automatically applied by the launcher in addition to those that are part of the request. As an example 8, we can consider this code segment, registering launcher session listener. The interface launcher session listener register an implementation of this interface to be notified when a launcher session is opened and closed. This in the module org.junit.platform.launcher and package org.junit.platform.launcher. Registered implementation of launcher session listeners are notified when launcher session is opened before launcher first discovered and execute test, and close when no more test will be discovered and executed. They can be registered programmatically via launcher config that is part of the launcher factory, or they can be discovered at runtime via Java's service loader mechanism and automatically registered with launcher session unless automatic registration is disabled. Tool support. Following build tools and IDEs are known to provide full support for launcher session, Gradle 4.6 and later, Maven, Surefire, Failsafe 3.0.0, M6 and later, IntelliJ IDEA 2017.3 and later. Other tools might also work but have not been tested explicitly. A launcher session listener is well suited for implementing once per JVM setup teardown behavior, since it's called before the first and after the last test in the launcher session respectively. The scope of the launcher session depends on the used IDE or build tool, usually correspond to the lifecycle of the test JVM. A custom listener that starts an HTTP server before executing the first test and stop it after the last test has been executed could look like this. Here you can see step 1 here, start server, and here you can see the export its host address as a system property for consumption by test, and export its port as a system property for consumption by test. And here stopped the HTTP server. The sample uses HTTP server implementation from the JDK HTTP server module that comes with the JDK, but it would work similarly with any other server or resource. In order for the listener to picked up by JUnit platform, you need to register it as a service by adding a resource file with the following name and context to your test runtime class path. For example, by adding the file to source/test/resources. Here source/test/resources meta-info/services org.junit.platform.launcher session listener. And the example.session.global setup tear down listener. Now you can use the resource from your test. Here HTTP tests. Here read the host address of the server from the system property set by the listener, and read the port of the server from the system property by the listener. Send the request to the server and check the status code of the response. And here you can see avoid setup for test discovery by delaying until tests are about to be executed. Registering launcher discovery listener. The interface launcher discovery listener register a concrete implementation of this interface with the launcher discovery request builder or launcher to be notified events that occur during the test discovery. This is in the module org.junit.platform.launcher and package org.junit.platform.launcher. Here in addition to specifying discovery listeners as a part of launcher discovery request or registering them programmatically via the launcher API, custom launcher discovery listener implementations can be discovered at runtime via Java service loader mechanism and automatically registered with the launcher created via launcher factory. For example, an custom launcher discovery listener class implementing launcher discovery listener and declared within /meta-info/services junit.platform.launcher discovery listener file is loaded and registered automatically. As an example 10, we can consider registering test execution listener. For example, an example.custom test execution listener class implementing test execution listener and declared within the /meta-info/services junit.platform.launcher.test execution listener file is loaded and registered automatically. The interface text execution listener register a concrete implementation of this interface with a launcher to be notified of event that occur during test execution. Module this is in the module org.junit.platform.launcher and package org.junit.platform.launcher. Here, in addition to launcher API method for registering test execution listeners programmatically, custom test execution listener implementation will be discovered at runtime via Java's service loader mechanism and automatically registered with the launcher created via launcher factory. As an example 11, we can consider junit.platform.execution.listener.deactivate. Here, deactivating a test execution listener. Sometimes it can be useful to run a test suite without certain execution listeners being active. For example, you might have a custom test execution listener that sends the test results to an external system for reporting purposes. And while debugging, you might not want these debugging results to be reported. To do this, provide a pattern for junit.platform.execution.listener.deactivate. Configure a parameter to specify which execution listeners should be deactivated that is not registered for the current test run. Only listeners registered via service loader mechanism within /meta-info/services/org.junit.platform.launcher.test unit test execution listener file can be deactivated. In other words, any test execution listener registered is explicitly via launcher discovery request cannot be deactivated via the junit-platform.execution.listeners.deactivate configuration parameter. In addition, since execution listeners are registered before the test run starts, the junit.platform.execution.listeners.deactivate configuration parameter can only be supplied as a JVM system property or via the JUnit platform configuration file. This configuration parameter cannot be supplied in the launcher discovery request that is passed to the launcher. As an example 12, we can consider configuring the launcher. The interface launcher config launcher config defines the configuration API for creating launcher instances via the launcher factory. This is in the module org.junit.platform.launcher and package org.junit.platform.launcher.core. If you require fine-grained control or automatic detection and registration of test engines and listeners, you may create an instance of launcher config and supply that to the launcher factory. Typically, an instance of a launcher config is created via the built-in Fluent builder API as demonstrated in this example here. Here, launcher config the builder create a new launcher config builder. Here the method test engine enable test engine auto registration in launcher config.builder class. Configure the auto registration flag for test engines. Here the enable launcher session listener auto registration. Configure the auto registration flag for the launch session listeners. Here enable launcher discovery listener auto registration. Configure the auto registration flag for launcher discovery listeners. Here enable post discovery filter auto registration. Configure the auto registration flag for the post discovery filters, and here enable text execution listener auto registration boolean. Configure the auto registration flag for the text execution text listeners. Here add test engines. Add all the supplied test engines to the configuration. Here add launcher session listeners. Add all the supplied launcher session listeners to the configuration. Add launcher discovery listeners. Add all the supplied launcher discovery listeners to the configuration. Add post discovery filters. Add all the supplied filters to the configuration. And add test execution listeners. Add all the supplied test execution listeners to the configuration. And the build the launcher config that has been configured via the builder. As an error example, we can consider this one occurred in IntelliJ and Spring Boot 2.3.9. Failed to resolve JUnit Platform-Launcher 1.6.3 IntelliJ. Now we are focusing on junit-platform.runner. junit-platform-runner. Runner for executing test and test suites on JUnit platform in a JUnit 4 environment. And as an example in Maven, we can consider this segment. Here you can see the artifact ID junit-platform-runner. This is in the group ID org.junit.platform. As an example 2, we can consider module org.junit.platform.runner and annotations for configuring and executing test on the JUnit platform in JUnit 4 environment. As an example 3, we can consider using JUnit 4 to run JUnit platform single test class JUnit platform JUnit 4 based runner, which runs test on the JUnit platform in JUnit 4 environment, deprecated since 1.8 in favor of the suite support provided by the JUnit platform suite engine module to be removed in JUnit platform 2.0 module. It is in the module org.junit.platform junit-platform-runner, package org.junit.platform.runner. Here one way to use the JUnit platform runner is to annotate a test class with ampersand run with junit-platform.class directly. Please note that the test methods with the following examples are annotated with org.junit-jupiter-api.test junit-jupiter, not org.junit.test junit-4. Moreover, in this case, the test class must be public. Otherwise, some IDEs and build tools might not recognize it as a junit-4 test class. The JUnit platform runner has been deprecated. The JUnit platform runner was developed by JUnit team as a interim solution for running test suites and test on the JUnit platform in a JUnit 4 environment. In recent years, all mainstream build tools and IDEs provide built-in support for running tests directly on the JUnit platform. In addition to the introduction of ampersand suite support by the JUnit platform-surefire-engine modules make the JUnit platform runner obsolete. The JUnit platform runner and ampersand use technical names annotation have therefore been deprecated in JUnit platform 1.8 and will be removed in JUnit platform 2.0. If you are using JUnit platform runner, please migrate to ampersand suite support. JUnit platform runner is a JUnit 4 based runner which enables you to run tests whose programming model is supported on the JUnit platform in a JUnit 4 environment. For example, junit-jupiter test class. Annotating the class with run with ampersand run with and JUnit platform.class allows it to be run with IDEs and built systems that support JUnit 4 but not yet support the JUnit platform directly. Since JUnit platform has features that JUnit 4 does not have, the runner is only able to support subset of JUnit platform functionality, especially with regard to reporting. The annotation type run with, when a class is annotated with ampersand run with or extend the class annotated with ampersand run with, JUnit will invoke the class it references to run the test in that class instead of the runner built into JUnit. We added this feature late in the development. While it seems powerful, we expect the runner API to change as we learn how people really use it. Some of the classes that are currently internal will likely be refined and become public. For example, suites in JUnit 4 are built using run with and a customer runner name suite. This description is with JUnit 4. So we can consider this code segment as example 4. Using JUnit 4 to run the JUnit platform test suite. If you have multiple test classes, you can create a test suite as can be seen in the following example. The annotation interface select packages, ampersand select packages specifies the names of packages to select when running a test suite on the JUnit platform. This is in the module org.junit.platform.suite.api and package org.junit.platform.suite.api. Ampersand suite display name is used to declare custom display name for the annotated test class that is executed as a test suite on the JUnit platform. As an example 5, we can consider this using JUnit 4 to run the JUnit platform setup. You need the following artifacts and their dependencies on the class path. Explicit dependencies: junit-platform-runner in test scope, location of the junit-platform-runner, JUnit 4.13.2.jar in the test scope to run the test using JUnit 4, junit-jupiter-api in the test scope, API for writing test using junit-jupiter, including ampersand test, etc. junit-jupiter-engine in test runtime scope, implementation of test engine API for junit-jupiter, transitive dependencies: junit-platform-suite-api in test scope, junit-platform-suite commands in test scope, junit-platform-launcher in test scope, junit-platform-engine in test scope, junit-platform-commands in test scope, OpenTest4j in test scope. As an example, we can consider this no test remain exception. Can be occurred in method void public void filter in class junit-platform. As an example, we can consider this occurred in environment with Eclipse and Maven. Package org.junit.platform.runner does not exist, etc. Now we are focusing on junit-platform-console. Support for discovering and executing tests on the JUnit platform from the console. Here you can see the artifact junit-platform-console. The group ID org.junit.platform. As an example 2, we can consider org.junit.platform.console module. Support for launching the JUnit platform from the console. As an example 3, you can also run the standalone console launcher as shown here. For example, to include all jars in a directory. Yeah. Exit code: the console launcher exit with the status code of 1 if any containers or test fails. If no tests are discovered and the --fail if -node -test command line option is applied, the console launcher exits with the status code of 2. Otherwise, exit code is 0. The class console launcher. The console launcher is a standalone application for launching JUnit platform from the console. It's in the module org.junit.platform.console and package org.junit.platform.console. The console launcher is a command line Java application that lets you to launch the JUnit platform from the console. For example, it can be used to run junit-vintage-engine Jupyter test and print test execution results to the console launcher. Argument files, ampersand files. If an argument contains embedded white space, the whole argument should be wrapped in a double or single quotes, for example. And options selectors -f or -- select -file equal file. Select file for test discovery. This option can be repeated. On some platforms, you may run into system limitation of length of the command line when creating command line with lot of options, so with long argument. Since version 1.3, the console launcher supports argument files, also known as ampersand files. Argument files are files that themselves contain arguments to be passed to the command. When the underline Picocli command line pass encounters an argument beginning with the character ampersand, it expands the contents of that file into the argument list. If the argument file does not exist or cannot be read, the argument will be treated literally and will not be removed. This will likely result in unmatched argument error message. You can troubleshoot such errors by executing the command with the pico-cli.trace system property set to debug. Multiple ampersand files may be multiple @signs may be specified on the command line. Specified path may be relative to the current directory or absolute. You can pass real parameter with the initial @character by escaping with the additional @symbol. For example, at some mark will become @some mark and will not be subject to expansion. As an example 5, we can consider color customization, the console launcher. The properties file here demonstrate the default style. The -- single color style test output using only text attributes, no color, not supported by all terminals. -- color -palette equal file specify a path to a properties file to customize and see style of output, not supported by all terminals. The colors used in the output of the console launcher can be customized. The option -- single color will apply a built-in monochrome style, while -- color -palette will accept the properties file to override NC SGR color styling. The properties file here demonstrate the default style here. Successful equal 32, aborted equal 33, failed equal 31, skipped equal 35, container equal 35, test equal 34, dynamic equal 35, and reported equal 37. As an exception example, we can consider this occurred in the environment with 5.0.0 and operating system and version Mac OS X 10.15.7 Catalina x86-64 build tools Gradle 6.8.3 Kotlin 1.4.30 JVM 11.0.10 and this is caused by Java. The console launcher test failed. The error could not find or load main class org.junit.platform.console launcher, caused by java.land.console class not found exception org.junit.platform.console launcher. Follow the steps for readme .md #cucumber -junit-platform-engine. Step 2, assume incorrectly that only dependency needed is org.junit.platform junit-platform-launcher xyz run /gradle clean test and observed error. As an error example, we can consider this occurred in the environment with JMeter and MSSQL-JDBC. Failure to find org.junit.platform junit-platform-console jar in https://repo.maven.apache.org./maven.was cache in the local repository. Resolution will not be reattempted until the update interval of central has lapsed or updates are forced. Now we are focusing on JUnit Platform-Surefire-Provider. JUnit Platform-Surefire-Provider, which provides a support for discovering and executing tests on the JUnit platform by using Maven Surefire. As an example in Maven, we can consider this one, artifact ID junit-platform-surefire-provider, the group ID org.junit.platform, the JUnit platform Maven Surefire-provider has been discontinued. The JUnit platform-surefire-provider, which was originally developed by the JUnit team, was deprecated in JUnit platform 1.3 and discontinued in 1.4. Please use Maven Surefire native support instead. Starting with version 2.22.0, Maven Surefire and Maven failsafe provide native support for executing tests on the JUnit platform. The pom.xml file in the JUnit Jupyter Starter Maven project demonstrate how to use Maven Surefire plugin and can serve as a starting point for configuring your Maven build. As an example too, we can consider package org.junit.platform.surefire.provider, Maven Surefire provider for JUnit platform. As an example 3, we can consider this Maven segment. Here you can see JUnit platform Surefire provider here. Now we are focusing on junit-platform-gradle-plugin. junit-platform-gradle-plugin, which provides support for discovering and executing tests on the JUnit platform by using Gradle. The junit-platform-gradle-plugin has been discontinued. The junit-platform-gradle-plugin developed by the JUnit team was deprecated in the JUnit platform 1.2 and discontinued in 1.3. Please switch to Gradle standard test task. As an example, we can consider this. Here you can see artifact ID junit-platform-gradle-plugin here. It's under group ID org.junit.platform. As an error example, we can consider this error occurred in environment Gradle version 4.0. Plugin with ID org.junit.platform.gradle.plugin not found. Now we are focusing on IDEs, build tools. An integrated development environment, IDE, is a software application that provides comprehensive facilities to computer programmers for software development. An IDE normally consists of at least a source code editor, built automation tools, and a debugger. Some IDEs such as NetBeans and Eclipse contain the necessary compiler, interpreter, or both. Others such as Sharp Develop and Lazarus do not. Build automation is the process of automating the creation of a software build and associated process, including compiling computer source code into binary code, packaging binary code, and running automated tests. As an example, we can consider IntelliJ IDEA. The IDE support. IntelliJ IDEA supports running tests on the JUnit platform since version 2016.2. Note, however, that it is recommended to use IDEA 2017.3 or newer, since these newer versions of IDEA will download the following jars automatically based on the API version used in the project: JUnit-platform-launcher, junit-jupiter-engine, and junit-vintage-engine. IntelliJ IDEA releases prior to IDEA 2017.3 bundle specific versions of JUnit 5. Thus, if you want to use a newer version of JUnit Jupyter, execution of tests within the IDE might fail due to the version conflicts. In such cases, please follow the different instruction to use newer version of JUnit 5 than the one bundled with IntelliJ IDEA. In order to use different JUnit 5 version, for example 5.9.0, you may need to include the corresponding versions of the junit-platform-launcher, junit-jupiter-engine, and junit-vintage-engine jars in the class path. As an example too, we can consider additional Gradle dependencies in IntelliJ IDEA here. As an example 3, we can consider Eclipse. Eclipse IDE offers support for the JUnit platform since the Eclipse Oxygen 0.1a 4.7.1a release. You can see the execution of test here. NetBeans, as an example 4, we can consider NetBeans. NetBeans offers support for JUnit Jupyter and JUnit platform since Apache NetBeans 10.0 release. As an example 5, we can consider Visual Studio Code. Visual Studio Code supports JUnit Jupyter and the JUnit platform via the Java Test Runner extension, which is installed by default as a part of the Java extension pack. As an example 6, we can consider Gradle build support here. Starting with version 4.6, Gradle provides native support for executing test on the JUnit platform. To enable it, you need to specify use JUnit platform within a test task declaration in the build.gradle junit-platform-gradle-plugin has been discontinued. The junit-platform-gradle-plugin developed by the JUnit team was deprecated in junit-platform 1.2 and discontinued in 1.3. Please switch to Gradle standard test task. As an example 7, in Gradle, we can consider this one, configuring test engines. To configure support for the JUnit Jupyter base test, configure a test implementation dependency on the dependency aggregating JUnit Jupyter artifact, similar to the following here. In order to run any test at all, a test engine implementation must be on the class path. As an example 8, we can consider Maven. Starting with version 2.22.0, Maven Surefire and Maven Failsafe provide native support for executing tests on the JUnit platform. The pom.xml file in the JUnit 5 Jupyter Starter Maven project demonstrate how to use the Maven Surefire plugin and can serve as a starting point for configuring your Maven build. JUnit platform Maven Surefire-provider has been discontinued. The JUnit platform-Surefire-provider, which was originally developed by the JUnit team, was deprecated in JUnit platform 1.3 and discontinued in 1.4. Please use Maven Surefire native support instead. As an example 9, we can consider Maven configuring test engines. In order to have Maven Surefire and Maven Failsafe run any test at all, at least one test engine implementation must be added to the test class path. to configure support for JUnit Jupyter based tests, test scope dependencies on the JUnit Jupyter API and the JUnit Jupyter test engine implementation similar to following. As an example 10, we can consider Ant. Starting with version 1.10.3, Ant has unit launcher task that provides native support for launching tests on the JUnit platform. The JUnit launcher task is solely responsible for launching JUnit platform and passing it to the selected collection of tests. The JUnit platform then delegates to registered test engines to discover and execute tests. As an example 11 in Ant, we can consider this segment, the basic usage. Here, this example demonstrates how to configure JUnit launcher task to select single test class, that is org.myapp.test.myfirstJUnit-test. As an example 12, we can consider Spring Boot. Spring Boot provides automatic support for managing the version of JUnit used in your project. In addition, the Spring Boot starter test artifact automatically includes testing libraries such as JUnit Jupyter, AspectJ, Mockito, etc. As an example 13, we can consider Spring Boot here. Configuration with Gradle. You can override the JUnit Jupyter version by including this in your build.gradle file. As an exception example, we can consider this. In Eclipse, the test would be marked as passed even if the test method throws an exception, which is a subclass of the specified exception in the at test expected clause. As an exception example 2, we can consider this occurred in environment with Gradle and JUnit. Error Gradle org.gradle messaging org.gradle.messaging.remote.intel internal.hub.message hub back to object connection, unexpected exception thrown, etc. and caused by java.land.nullPoint exception at java.land.throwable set stack trace throwable at org.gradle.messaging.remote.internal message exception placeholder.read. As an error example, we can consider this occurred in the environment with IntelliJ IDEA, Maven, and JUnit 5 here. And you can see process finished with exit code -1 here. As an error example 2, we can consider this occurred in environment with Gradle. Here compile Java, users workload project gradling source test calculate test.java error package org.junit does not exist, etc. And here 5 errors and compile failed, failure, build failed with an exception, etc. This is end of my presentation. Thank you very much for watching it.